Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. Last time we spoke quite a bit about degrees of freedom and the idea that once we define a certain number of phase-intensive properties characterizing a system of molecules, all other intensive properties are determined by equilibrium. But what are these properties, and how do workers go about describing the relationships among them? To start, let's focus primarily on experimentally observed relationships, and limit ourselves to the behavior of pure substances, meaning systems with just one molecular species. As we'll see, many of the approaches used for pure substances are readily extendable to similar problems in mixtures, so it's a great place to begin. I'd like to start today's episode with a quote by the famous physicist Richard P. Feynman, who in 1963 published a series of lectures for undergraduate physicists. In the first chapter, he says that the test of all knowledge is experiment, but also needed is imagination to theorize the wonderful, simple patterns beneath the data. He goes on to say that this imagining process is so difficult that there is a division of labor in physics. There are theoretical physicists who imagine, deduce, and guess at new laws, but do not do experiments. And then there are experimental physicists who experiment, imagine, deduce, and guess. I love this quote, not only because it reveals Feynman's self-deprecatory sense of humor — he was, after all, one of the great theoretical physicists of the 20th century — but he's also making a point, which is that theoretical understanding of something does not really begin with a bunch of equations. It starts with how we think about and describe physical relationships based on experimental observations. And this is just as an important an element of our theoretical understanding of something as the equations we ultimately use to describe those relationships. So today, let's begin by developing an understanding of state property relationships in pure substances by looking at some of the typical ways workers describe these relationships using phase diagrams and tabulated data. One of the systems we looked at last time was H2O inside a transparent piston cylinder assembly. According to Gibbs' phase rule, with only one phase present, water, we should have 2 degrees of freedom, meaning that we should be able to vary the temperature and molar volume of the liquid independently, while all other properties are a response due to equilibrium. We saw this played out experimentally when we fixed the temperature at 25 degrees C and varied the volume slightly and saw a large response in terms of the pressure. One way to visualize this is to make a plot of pressure versus molar volume. Starting at our initial point, V0 and P0, we then varied volume slightly and saw these large changes in pressure as an almost vertical PVT surface. However, as we continue to expand the volume, beyond a certain threshold, the water, instead of expanding uniformly, splits into 2 phases, a liquid and a gas. According to Gibbs' phase rule, with 2 phases present, we only have 1 degree of freedom, which we've already consumed by setting the temperature at 25 degrees C. Thus, pressure should be a consequence of equilibrium at that temperature. Indeed, we saw the pressure stopped changing and became a constant at this temperature. Returning to our plot, this corresponds to a leveling off of pressure at a constant value as we continue to increase the volume at fixed temperature T1. Recall we called this pressure the saturation pressure. We also saw that as we vary the temperature from 25 degrees C to 60 degrees C and so forth, that the saturation pressure was a function of temperature, increasing as we increase the temperature. We summarize these data by making a plot of the saturation pressure as a function of temperature. This plot is a type of phase diagram called a PT diagram, since it maps out the different phases of H2O that will form under different conditions of temperature or pressure. At combinations of pressure and temperature above our saturation data, the H2O remains a single-phase liquid with 2 degrees of freedom. However, when the pressure drops low enough to intersect the saturation line, also known as the coexistence curve, the system splits into 2 phases with 1 degree of freedom. As long as 2 phases are present, any changes in pressure must accompany a change of temperature. Looking more broadly, this is a PT diagram for H2O over a much wider set of conditions, spanning 0 to 1000 Kelvin and 10 to the minus 6 to 10 to the plus 7 atmospheres. To put things in perspective, the PT diagram that we looked at previously corresponds to this small area right here in the middle of this phase diagram. This diagram shows that H2O can exist in many forms, including what we think of traditionally as liquid and gas, but also as a fluid having properties intermediate between liquid and gas, as well as a variety of solid phases of differing crystal structure. At moderate pressures, near where our experiment was, H2O tends to obey our traditional concept of boiling. If the system starts as a high-density liquid and we heat at constant pressure, it will boil, forming a low-density gas. If we cool again, it will recondense back into a liquid. The transition in density from liquid to gas is abrupt, occurring at a particular temperature we call the boiling point. At higher pressures, however, it is possible to lose this clear distinction between liquid and gas. For example, imagine we start at the same point we just did, but before heating we increase the pressure to 100 megapascals or so, then heat, then lower the pressure, then finally cool to the same state as before. Note that the water and steam at the endpoints of the transition are the same as we had before, since pressure and temperature are state properties. However, along this alternate path, the water never actually boils. The density changes smoothly and continuously from high to low along the transformation path. The pressure and temperature beyond which we no longer observe a distinct liquid and gas is known as the critical point, which for water occurs at 374 C and 220 bar. Fluids at pressures and temperatures above the critical point are often described as supercritical fluids. One of the things we'll explore this quarter is why substances switch from having smooth, continuous behavior like this to having a distinct liquid-gas transition. This PT diagram also shows a number of solid phases. The one you're probably most familiar with is ice 1H, which forms naturally by cooling liquid water at moderate pressures. The temperature at which ice 1H forms is called the freezing point or melting point, depending on which direction the transition occurs. This diagram shows that you can also make solid H2O at ambient temperature by increasing the pressure of liquid water until it reaches about 20,000 bar. Note that the solid that forms under these conditions is not ice 1H, but another crystal structure, either ice 6 or ice 7, depending on the exact temperature. Unlike regular ice, these solid phases are denser than liquid water, so sink to the bottom of the container in which they precipitate, rather than floating on top. As we'll see, the orientation of the coexistence line between liquid and solid is closely related to these changes in density, among other factors. Finally, we also see that at several points on the diagram, three different phases can coexist. An example is the triple point, defined as the conditions where solid, liquid, and gas can remain in equilibrium indefinitely. According to Gibbs' phase rule, with one component and three phases, the number of degrees of freedom is 0, meaning that all phase-intensive properties, including temperature and pressure, are determined by equilibrium. Hence, for a given group of three phases at equilibrium, this situation can only prevail at a single point on a PT diagram. Unfortunately, this PT diagram only shows the coexistence curves, so it's not possible to see what's happening to the values of other intensive properties, such as volume. However, one way to visualize this is to imagine the PVT surface for the fluid, which can be done even when more than one phase is present. For many substances, between the triple point and the critical point, this surface looks something like this. Along most of this surface, volume varies continuously with temperature and pressure, but when more than one phase is present, the surface becomes parallel to the volume axis, meaning that volume can change without a change in temperature or pressure. A PT diagram is basically a 2D projection of this PVT surface when viewed along the volume axis. From this viewpoint, the two-phase areas appear to be lines corresponding to the coexistence curves for solid plus liquid, solid plus gas, or liquid plus gas. These surfaces intersect along a line called the triple line, which when viewed along the volume axis becomes a single point on the PT diagram. Meanwhile, the critical point corresponds to the outermost edge of the liquid-gas region, beyond which the PVT surface is no longer parallel to the volume axis. For example, Imagine the system starts as a liquid at moderate temperature and high pressure. It then undergoes a transformation path that takes it up in temperature, beyond the critical point, down in pressure, and then back down in temperature and pressure until it reaches a final state at its original temperature and low pressure. Along this path, the molar volume increases smoothly from point to point along the PVT surface. In contrast, if the system instead takes an isothermal transformation path, meaning constant temperature, between the same 2 points, the liquid will instead begin to boil somewhere in the middle of this path. For as long as it takes all the liquid to turn into a gas, the volume will change discontinuously, meaning without any change in temperature or pressure, corresponding to a single point on the PT diagram. An isothermal transformation path like this is also called an isotherm. This figure shows that the critical temperature is the lowest isotherm, where the volume can still change smoothly and continuously from high to low pressure. We can also view the PVT surface and isotherm along the temperature axis. This results in another type of phase diagram called a PV diagram. Unlike a PT diagram, where 2 phases can only exist simultaneously along one of the coexistence curves, a PV diagram shows a 2-dimensional projection of the PVT surface where more than one phase are present. This is called a two-phase region, sometimes labeled as shown here with the identity of the 2 phases present at equilibrium. Within this region, the volume becomes a system-intensive average rather than a phase-intensive property of either phase. For this reason, the isotherm takes a sharp bend as the system goes from liquid to liquid plus gas, just as we saw experimentally for water in the transparent piston cylinder assembly. To help us understand this a bit more thoroughly, let's take a closer look at an example from Chapter 1 of our book, in which the author, Milo Koretsky, discusses what happens to a liquid being heated at constant pressure from liquid to gas. In this example, the pressure is being held fixed as we slowly add heat, changing temperature and/or volume as the system remains in a continuous state of equilibrium. Using what we've learned so far, let's try to work out what this transformation looks like on a PT and a PV diagram. As we've discussed, in either single-phase region, we have 2 degrees of freedom, meaning that if we fix pressure, we can still vary temperature. Thus, as we add heat to the liquid, it will increase in temperature following the blue trajectory shown on the PT diagram. On the PV diagram, this trajectory corresponds to a slight increase in volume, but due to the small thermal expansivity of liquids, this change will be very small. Likewise, when the system only contains a gas, it will increase in temperature and volume as heat is added, following the green trajectory shown on the PT and PV diagrams. However, when 2 phases are present, there's only 1 degree of freedom. Thus, if we constrain pressure, the temperature and mass-specific volumes of the liquid and gas are determined by equilibrium. As we add heat to the system, the temperature will stay fixed, but the amount of gas will increase due to absorption of latent heat. On the PV diagram, this corresponds to an increase in the system-intensive volume, which changes in proportion to the amount of gas present in the system. This transition appears as a single point on the PT diagram, corresponding to the boiling point of the liquid at the imposed pressure, P0. So how do we relate the system-intensive volume to the extent of boiling? For example, if we pick a mass-specific volume V3, which is in between V liquid and V gas, how is this related to the amount of each phase? Well, as we saw in a previous episode, we can always express the average mass-specific volume of the system as a whole to the extensive volumes and masses of the individual phases. Rearranging, we find that the system-intensive volume is a linear function of quality, the fraction of the system mass that is gas versus liquid. This is exactly what we saw previously with an equilibrium mixture of saturated salty water and solid salt. This basic idea can be generalized in terms of something called a tie line. A tie line is a line connecting 2 points at the edges of a 2-phase region, corresponding to the intensive properties of the 2 individual phases that are in equilibrium. On a PV diagram, all tie lines are horizontal, since at equilibrium the 2 phases must share the same pressure. They also share the same temperature, implying that the tie line also lies along an isotherm. However, unlike a single phase region, where volume corresponds to the phase-intensive volume of a particular phase, the volume in the two-phase region does not correspond to any actual substance. Rather, the position along the tie line is related to the relative amounts of the two phases, which have fixed properties given by the endpoints of the tie line. Relating this amount to quality and rearranging, we can see that the quality is directly related to the relative position along the tie line. If the volume is far to the left, close to the volume of the liquid, the system contains mostly liquid. If the volume is far to the right, close to the volume of the gas, then the system contains mostly gas. In fact, if the axis used to indicate volume is linear, the fractional position along the tie line, as measured using a ruler, is directly proportional to the quality. Okay, so hopefully most of this makes sense to you. But so far we've been thinking conceptually, examining cartoons of a PV diagram. What does a real PV diagram or other related phase diagrams actually look like? As an example, here is a log P versus log V diagram for H2O constructed from actual data from the steam tables. To orient ourselves, here is the region of the diagram roughly corresponding to the conditions in our transparent piston cylinder assembly. Transferring our data for the 60° C isotherm to this plot, it falls about here with a vertical portion inside the liquid region and a horizontal line inside the two-phase region. Here's the rest of the 60° C isotherm. Even on this log-log plot, it's not possible to discern any changes in volume for the liquid at this temperature, reflecting its near incompressibility. In contrast, pure gaseous H2O at 60 C, outside the two-phase region, varies nearly linearly on a log P versus log V diagram, for reasons I'll explain in a moment. Here's another isotherm at 200 C. At this temperature, slight volume changes in the liquid become more apparent, while the gas remains very similar. Finally, here's an isotherm at 400 C, about 25 C above the critical temperature. You can see that under these conditions, there is no longer a distinct transition from liquid to gas. The supercritical H2O transitions smoothly from a high density to a lower density fluid, eventually becoming a gas with a PV trajectory similar to what we saw at lower temperatures. Taking a closer look at this trajectory, we see that it closely follows a line of slope -1 on this log-log plot. Why is this? Well, recall the ideal gas law. It predicts that when temperature is held fixed, as it is along one of these isotherms, the pressure will vary inversely with volume. If we take the log of this relationship, it predicts that log P will vary with log V with a slope of -1, exactly what we see in the data at large volumes. As we'll see in a couple of episodes, this ideal behavior at large volumes can be nicely explained in terms of the strength of short-range molecular interactions, which become weak when the molecules become far apart. Another quantitative feature you might notice on this diagram is the slight inward kink in the boundary of the two-phase region as it crosses the triple line. This kink is opposite to what is shown on the generic PVT surface that I showed you previously. This is because, unlike most other substances, which expand upon melting, H2O expands when it freezes. Thus, the PVT surface of H2O looks more like the one on the right, with a solid liquid coexistence line that extends up and to the left of the triple point. We'll come back to understanding this in more depth later in the quarter. Returning to the PV diagram, one thing to point out is that this diagram only really shows PVT relationships. According to Gibbs' phase rule, once we've set two intensive properties, or one if we're in the two-phase region, all the other properties like enthalpy, entropy, and so forth are determined by equilibrium. So where are these properties on the diagram? Well, it turns out that when workers are interested in these other properties, they usually plot the data differently. In particular, for properties involving the design of power or refrigeration cycles, a common type of phase diagram used is a pH diagram, which for H2O liquid and gas is shown here. On a pH diagram, the two independent variables are pressure and enthalpy, while other properties are shown as contours. Like a PV diagram, a pH diagram has a two-phase region corresponding to equilibrium of a low enthalpy liquid and a high enthalpy gas. Shown in yellow is the boundary of this region, including the critical point. Also plotted on this diagram is temperature, shown as a series of isothermal contours, or isotherms, corresponding to the equilibrium temperature at that point on the diagram. As with the PV diagram, these isotherms are horizontal in the two-phase region, corresponding to the loss of 1 degree of freedom and dependence of saturation pressure on temperature. Other properties plotted in this diagram include mass-specific volume and entropy, shown as a series of isochoric contours, meaning lines of constant volume, and isentropic contours, meaning lines of constant entropy. Finally, I should also point out that any horizontal or vertical lines drawn on the pH diagram correspond to isobaric or isenthalpic contours, meaning lines of constant pressure or enthalpy, respectively. The benefit of a phase diagram like this is that it has everything in one place, and for some problems can be valuable for visualizing molecular transformations in a particular problem. However, as you can see, things tend to get a bit messy when all the properties are plotted on top of each other. Also, with a graph, we're limited to a couple of significant figures at best, as well as the accuracy limitations of interpolating between contours. For this reason, when we really need to calculate something, we often switch from a phase diagram, which gives us a nice big picture of what's happening, to tabulated data, which cannot be easily visualized, but has the benefit of defined accuracy. A prime example of this is the steam tables, which report the thermodynamic properties of H2O. You'll find many of these in Appendix B of our textbook. Some of these tables cover the properties of single-phase H2O as a liquid or gas. These have the somewhat odd traditional names of superheated steam and subcooled liquid. When I first read these names as a student, I found them quite confusing, since I didn't understand what was special about being superheated or subcooled that made it different from regular steam or regular liquid. That was until I realized that these terms really don't mean anything. They're just a reference to the state of the H2O as a single phase above or below the saturation temperature. What these terms really mean is either gaseous H2O, steam, or liquid H2O, water. I emphasize the word or since the properties of gas and liquid are quite different, so appear in separate tables. With either gas or liquid alone, Gibbs' phase rule tells us that we need to specify two independent intensive properties to define the state of the H2O. We expect the structure of our tables to reflect this two-dimensionality in some way. For gaseous H2O, for example, this is accomplished by having a series of tables, each of which corresponds to a particular pressure. Then within each table, each row corresponds to a particular temperature. Other properties, including the volume, internal energy, enthalpy, and entropy, are then tabulated in adjacent columns as a function of temperature and pressure. By interpolating between entries in adjacent rows or tables, we can obtain properties at conditions that fall in between the entries or back-calculate values of temperature and pressure at particular known values of other properties. In contrast, when both a liquid and a gas are present at equilibrium, also known as a saturated state, we only have 1 degree of freedom, so only expect properties to be reported as a function of one intensive variable. For convenience, the data are actually tabulated both as a function of temperature or pressure, but the data in these tables is really redundant. For the temperature table shown here, each row corresponds to a different temperature. The adjacent column shows the saturation pressure corresponding to each temperature along the coexistence curve. Then in the other column are the intensive properties of the two phases. These include the volume, internal energy, enthalpy, and entropy of the liquid, and the volume, internal energy, enthalpy, and entropy of the gas. Also reported in the column in between is the change in that property between the liquid and gas, delta H of vaporization, for example. Before we go on, I'd like to just remind you how to interpolate a table like this. For example, let's say we want to know the saturation volume of gaseous H2O at 97 degrees C, which falls in between 95 and 100 degrees on the table. Usually the intervals between rows is chosen to give a predicted accuracy if interpolated linearly. With linear interpolation, we assume that between rows adjacent to our point of interest, the volume changes linearly with temperature. If so, we can say that the relative position of temperature between these 2 points is the same as the relative position of the volume. After calculating this known position, in this case 0.4 of the way from one point to the next, we can apply to the volume to find the point in between. For some properties or excessively large intervals between points, It's sometimes advisable to retabulate other quantities before interpolating linearly. For example, log of the saturation pressure versus reciprocal temperature. But we'll come back to this issue a bit later. Okay, so that's water. But what about other substances? You can always go to the open literature, but often the data you're interested in may be scattered among multiple sources or buried in papers that are difficult to retrieve. To help us out, the National Institute of Standards and Technology, NIST, has kindly consolidated thermodynamic data from many common substances on their website in a database called the NIST Webbook. Just Google NIST Webbook with 2 B's and you'll find it. Let's go through a brief tutorial on how to use it. Okay, so from the main site, what you'll want to do is first pick the link, scroll down to the link that says Thermophysical Properties of Fluid Systems. Click on that. Shows you all the properties that it contains. And the first thing we have to do is pick a compound, which in this case, I'm going to keep it simple and pick water to be comparable to the steam tables. And then the next thing we pick units. So again, to be consistent, I'm going to pick Celsius, bar, kilogram per meter cubed, kilojoules per kilogram, put it in mass specific units. And then down here, we have to pick whether we want single phase or two-phase systems, picking either isobaric or isothermal properties. If we pick isobaric, what it means is we're picking a single pressure. In this case, I'm setting it 1 bar, and then we look at the other variable as a range, in this case 25 to say 175 degrees C in 1 degree increments, and then press for the data. And right after this, we're greeted with a plot showing the properties, in this case temperature, as a function of temperature, the density. I can also switch to any other property for the fluid in that temperature range, either liquid or vapor, depending on the conditions. I can also hit HTML table, and that'll give me all the properties in a nice tabulated form, very similar to the steam tables. In this case, holding pressure constant at 1 bar and varying the temperature. Notice the reference state for this system of, for this group of data is what's selected by default. You can also pick other reference states. Okay, so we're also might be interested in saturation properties. To do that, go back to this page, and instead of picking isobaric, I'm going to pick saturation properties, temperature increments, press the data. In this case, we just give a temperature range. I'm going to go from 0.01 degrees C up to 373 degrees C, and press for data. And this time it gives me a plot which shows properties of both phases which are present at the same time in the system. So as a function of temperature, for example, it's showing right now the pressure, which is a single property for both phases. I can also switch to phase-intensive properties like the vapor volume. It also shows the liquid volume on the same plot at the same temperature. Switching to another variable, we can also look at other properties. For example, the enthalpy shows the liquid and vapor enthalpy that we have in equilibrium. The blue line being the liquid, the low enthalpy phase, and the upper line, the red line, being the vapor enthalpy, which is higher than the liquid enthalpy at equilibrium. Again, I can hit the HTML table, and that will now give me the data in tabulated form. In this case, it produces 2 different tables, one for liquid saturation, and then the other for vapor saturation data. So giving all the phase-intensive properties for each phase separately at the same set of temperature and pressure conditions. Okay, so this concludes our initial tour of thermodynamic properties in systems with a single component. However, to make things a bit more concrete, let's now focus on a couple of specific examples so you can see in a bit more detail how things actually work. These problems require us to combine thermodynamic principles with 310-style mass and/or energy balances, which most of you are familiar with already. One of the things we discussed earlier is the concept of a tie line, which appears on any phase diagram with one or more system-intensive properties as an independent variable. Let's start by thinking about a PV diagram and how a tie line can be used to conceptualize the equilibrium state of H2O in a two-phase system. In particular, imagine we place 1 gram of pure H2O inside a rigid closed container of volume 1,000 cubic centimeters, and add or remove heat until the equilibrium temperature reaches 60 degrees C. What phases will be present in our container at equilibrium? At what pressure? And in what quantities? Note that in this case we know the total mass and volume of the H2O in the system, so can directly calculate the mass-specific volume of the system. After some unit conversion, this value is 1 cubic meter per kilogram. That's about 1,000 times less dense than water, approaching the density of a gas at 1 atmosphere under ambient conditions. So the first thing we need to figure out is whether the system will have two phases, a liquid and a gas, or will just have one phase because all the H2O evaporates inside the container. Turning to the PV diagram we introduced earlier, we can look along the 60 degrees C isotherm to see what is possible at this temperature. This isotherm shows that for mass-specific volumes greater than about 8 cubic meters per kilogram, the H2O will be single phase and have a pressure-dependent molar volume. However, for volumes less than 8 cubic meters per kilogram, the H2O cannot remain a single phase and must partially condense to satisfy the overall volume constraint in our system. Since the system-intensive volume of the H2O is only 1 cubic meter per kilogram, we can safely conclude that we must have two phases. With two phases present, the pressure is determined by equilibrium at 60 degrees C, which is about 0.2 atmospheres according to this diagram. Thus, the remaining question is, how much of each phase will we have in the system? Drawing a tie line, we can estimate the mass-specific volumes of the liquid and gas to an accuracy of about one significant figure, 0.001 cubic meter per kilogram for the liquid, and about 8 cubic meters per kilogram for the gas. The system as a whole, at 1 cubic meter per kilogram, lies about 1/8 of the way along this tie line. Note that on the log-log plot, it looks visually like the system is about 3/4 gas, but this is an illusion created by the logarithmic axes. To determine the quality, we need to look at the actual numbers. Doing so yields a quality of about 0.1, meaning 10% of the mass of the system is gas, while 90% remains liquid. This is about as accurate as we can be given the level of significance of the values taken off the phase diagram. Now that we've used the phase diagram to figure out what's basically going on, one way to gain more certainty in our calculation is to consult the steam tables. Looking up the saturation properties of H2O at 60 degrees C, we find a saturation pressure of 0.20 bar and a mass-specific volume for the liquid and gas of 1.017 times 10 to the minus 3 and 7.67 meters cubed per kilogram, respectively, for the liquid and gas. Recalculating to two significant figures, we can conclude that the system will be 13% steam and 87% water at equilibrium. This was an example of a volume-constrained system, so very appropriate to solve using a PV diagram. However, many times in thermodynamics, our analysis involves some kind of energy transformation. In these cases, phase diagrams with other formats, like a pH or TS diagram, can be much more useful. As an example, consider the following problem involving part of a refrigeration process. Liquid refrigerant R134A at 10 bars and 25 degrees C, stream 1, is expanded adiabatically through a throttling valve into an insulated flash drum, where it reaches equilibrium at 1 bar. Gas generated by this flash operation exits in stream 2, while the remaining liquid exits in stream 3. We'd like to know the final temperature of the fluids exiting the flash drum, and how much of the original refrigerant exits as gas versus liquid. So first of all, why do we expect the refrigerant to get cold in the first place? Since the flash is adiabatic, there's no way for heat to exit the fluid. So somehow the fluid gets colder, less kinetic energy, by converting this kinetic energy to some other form. As we'll discuss next week, this energy is converted into potential energy by increasing the average distance between molecules by partially vaporizing the liquid. We expect this conversion of kinetic to potential energy to be reflected in some way in the equilibrium data. Shown here is a pH diagram for R134A refrigerant. The state of stream 1 is located in the single-phase liquid region, which we can find by looking for the intersection of the 25 degrees C isotherm and the 10 bar or 1 megapascal isobar. Meanwhile, if we're correct about the liquid splitting into two equilibrium phases at 1 bar, the states of streams 3 and 2 will sit at the ends of a tie line located in the two-phase region at 1 bar, or 0.1 megapascals. Sketching in an isotherm corresponding to this saturation pressure and interpolating between isotherms, it looks like the equilibrium temperature in the drum will be about minus 27 degrees C. This corresponds to the liquid inside the drum as well as the temperatures of streams 2 and 3, which leave the drum in equilibrium. The next question is how much gas versus liquid. Note that since we're converting kinetic to potential energy, we might expect to be able to solve this with an energy balance around the process as a whole. Since this is an open system at steady state, this balance involves the enthalpies of the streams entering and exiting the process in streams 1, 2, and 3. Consulting our phase diagram again, we see that the mass-specific enthalpies of the fluids in streams 3, 1, and 2 are 14, 85, and 233 kilojoules per kilogram, respectively. Drawing our control volume around the entire process, and recognizing there is no heat or shaft work, our extensive mass and energy balances look like this. We don't know the mass flow rates in any of the streams, so this is an underdetermined problem. However, we don't care in this case about the absolute flow rates, we just need to know the ratio of the outgoing gas flow to the incoming liquid flow, m2 dot divided by m1 dot. Solving, and recognizing that the enthalpies of streams 2 and 3 are the pure phase values for the saturated gas and liquid, we see that this ratio looks a lot like the quality calculation we did previously for a system of defined volume. This leads to another way of thinking about the same problem. Streams 2 and 3 really just involve physical separation of the gas and liquid in equilibrium in the flash drum. Thus, the ratio of M2 to M1 is just going to be equal to the quality of the two-phase mixture inside the flash drum. Meanwhile, the system-intensive state of the mixture inside the drum can be visualized as a point somewhere along the tie line between the liquid and gas. Since the valve is adiabatic, this point must share the same enthalpy as the incoming liquid in stream 1, 85 kilojoules per kilogram. Thus, we can equivalently calculate the quality as a relative position of this enthalpy along the tie line, just as we can for volume. In fact, this approach works for any system-intensive molar property, including volume, enthalpy, internal energy, entropy, and so forth. Which we use depends on the constraints of our particular problem, and thus which of these system properties we have knowledge of. In the last problem, it was molar volume. In this case, we have an open system energy balance telling us the enthalpy of the fluid in the flash drum. The net result is that about 32% of the refrigerant entering the system will exit as vapor in stream 2, while 68% leaves as liquid. As with the previous problem, we might like to check our interpolation of the phase diagram by checking numbers from the NIST database. Selecting asymmetric tetrafluoroethane, which is what R134 is, let's first plot values for the single-phase liquid at 10 bar between 20 and 30 degrees C. Looking at 25C, we find a value of 234.6 kilojoules per kilogram. Switching now to saturation properties, we can also plot the saturation values for gas and liquid between 0.5 and 1.5 bar. Looking first at the saturation temperature at 1 bar, we see that the temperature in the drum will be minus 26.4 C, pretty close to our previous estimate. Meanwhile, the enthalpies for the liquid and gas are 165.4 and 382.6 kilojoules per kilogram. Plugging these values back into our previous calculation, we obtain a quality of 0.319, or 31.9% gas, also fairly close to our estimate based on the data from the phase diagram. Note that the values of enthalpy that we used here are about 150 kilojoules per kilogram higher than the values from the phase diagram. This is because the default reference state used in the NIST database is different from the triple point reference state used in the phase diagram. This difference cancels out in our calculation, so from a practical standpoint doesn't matter. However, this difference does illustrate how things could potentially go wrong in our calculation if we ever mix data from different sources. We'll talk more about this issue in a few weeks when we cover measurements and calculations of energy and entropy and the importance of working with a consistent reference state. Finally, as a follow-up question, let's consider the case of R134A at 100 C and 1 bar expanding adiabatically through a throttling valve to 0.5 bar. Do we expect this gas to cool off in the same way as the liquid refrigerant when allowed to expand through the valve? Consulting the phase diagram again, we find our initial state in this case is in the single-phase gaseous region at the intersection of the 0.1 megapascal isobar and the 100 degree C isotherm. Expanding at constant enthalpy once again, we find that at the final pressure of 0.5 bar, the temperature in state 2 is 100 degrees C, exactly the same as in stream 1. In other words, the gas does not cool in the same way as a liquid refrigerant did. Why is this? Well, as we'll discuss more next week, this goes back to the issue of potential versus kinetic energy. For the expanding liquid, adiabatic expansion results in a conversion of kinetic to potential energy as the mixture becomes partially vaporized, and many of the molecules become separated. However, in a gas at low pressure, the molecules are already separated, and thus in the highest state of potential energy they can be. Further expansion offers no mechanism to convert kinetic to potential energy. This and other issues related to interactions among molecules are at the core of why groups of molecules behave as they do, and something we'll explore over the rest of the quarter.